Welcome to the slide series, A Visual Approach to Optics, A Guide for Clinicians by Drs. John Gorfinkel, Sharif El-Dafraoui, and John Lloyd, Faculty of Medicine, University of Toronto. This series is made up of 11 episodes of about 30 minutes each. The series is based on diagrams. Each slide has one diagram, and there are a total of 278 slides. The chapters are divided up into physical properties of light, geometrical optics, prisms, magnification, vision tests, optical instruments, and selected topics more in depth. The last chapter is selected topics in more depth at a stage when there is more understanding of the material. A page title that includes the phrase "for those interested" indicates a topic that may be of interest to some readers, but is not basic material for clinical purposes. Chapter 1: Physical Properties of Light. Light has both particle and wave-like properties. Particle-like properties have each photon as a fixed quantity of energy, so that the intensity is proportional to the number of photons per unit time. Electrons may also absorb photon energy and go to a higher energy state, and they may generate photons as they drop to a lower energy state. For our clinical purposes, a better model is light as an electromagnetic wave. In this model, we have light spreading out from the point of origin in spherical wavefronts in 3D, shown as circular in 2D. The intensity would be proportional to the amplitude of the waves. Diagrams showing the waves are indicated by circles, showing the crests of each wave. In between each crest, there is a trough, which is not shown on the diagram, but is halfway between the crests. The color of light is determined by its frequency, so that the blue light has a higher frequency and a shorter wavelength than red light. In a particle model, one would expect that light would be able to enter through an aperture and light up a panel behind it, but not spread out beyond the borders of the opening, as is actually seen, and this can be explained by the wave model. The electric field of light waves varies with the distance from the point of origin in a sinusoidal manner. It also varies with time at any one point. Frequency, nu, is inversely proportional to the wavelength, 1 over lambda. The color spectrum of light varies from 400 nanometer to 700 nanometer in wavelength. That is the distance between each peak or each trough. One can see from the electromagnetic spectrum that the visible portion is actually quite small. Electromagnetic radiation of much longer wavelength can be seen in the radio frequencies, and much shorter wavelength and much higher energy in the X-ray and cosmic ray end of the spectrum. Color perception of light. White light is made up of a spectrum of all colors of light. When we try to simulate white light on a computer screen, we can light up the red, blue, and green pixels in a proportion to give the impression of white light. Orange light, on the other hand, has a different proportion of these three colors lit up on the screen. The reason this method works is because our 3 color cones respond differently to each color of light. So that orange would stimulate the blue cones the least, the green cones more, and the red cones the most. And we can simulate the orange color with 3 colors of pixels by using a proportion as shown. As waves of light move out from the point of origin in a spherical manner, the surface area increases. The electric field density per unit of surface area, therefore, decreases. The irradiance, which would be the power shown in watts per centimeter squared, would be a measure of a way of measuring brightness. However, illuminance more accurately represents our human perception, in that we do not respond to all colors of light equally, as our cones are preferential to certain colors. Light wave representation of waves versus rays is shown here. Most textbooks will simply show you a series of arrows and say that light rays are spreading out from the point of origin. However, these light rays are just a directional indicator of where the corresponding parts of each wavefront are as they move out. One should think of it, what light really is, as waves. And arrows are just a way of representing the directionality of different parts of the waves. The wavelength, lambda, is the distance between each wave. Note that the curvature of the waves of light goes down. It becomes less curved as it moves away from the point of origin. In later slides, you will see that in geometrical optics, we often only show the arrows to represent the movement of the waves. We show only the arrows because they are more convenient for calculating certain numbers like object image size and magnification and divergence and so on, than using the circles. So if one thinks of a wave of light like a row of marching runners, they move forward in formation. As one can see, if each runner stays along a straight path, but they go at the same speed, they maintain their relative configuration. However, they're spreading out as they move out. The crest of each wave is shown here, whereas the troughs in between are not. Here we see what happens when waves of light are approaching an object shown here, a lens. The lens has a curved surface and a higher index of refraction than the surrounding medium. What we need to know at this point is just say that the runners are marching at a constant speed, but as soon as they enter the glass, they slow down. Later, when they leave the glass, they speed up. As you can see, the runners in this line reach the glass sooner than the runners in that line. They slow down earlier than the runners over here and over here, because the runners in the periphery are still moving faster in air. Eventually, they do reach the glass. By then, the middle runner here has moved more slowly, and the configuration of the runners has changed and become less curved. And by the middle, they are all in line. They start to move at an equal speed within the glass at this point, but the ones in the periphery exit the glass sooner than the ones in the middle. they start to run ahead of the runners in the middle, and the configuration between the runners therefore changes. Now it is in the opposite configuration. It was a concave expanding configuration before, and now they're in a convex contracting configuration here. The runners will eventually meet at a point, and this is analogous to an image point. An object point where the light begins, and here is an image point where the light is concentrated once again and ends. Here is another representation of waves moving forward, encountering a lens. Soon, those parts of the wave that enter the lens move more slowly in this diagram, and therefore results in a change in configuration. In this way, we can take what we call expanding or diverging light and turn it into contracting or converging light. You can see that the light energy is spreading out, but the part of the light that goes through the lens is then concentrated once again until it reaches an image point. Note that the part of the waves that passes to the side of the lenses remains and continues to expand indefinitely. In this area, there is no light. There are shadows. So where did the light go? Actually, the light is all here, but it's being more concentrated as it's approaching an image point. This therefore leaves a shadow on either side. The speed of light in a vacuum is given as c. The speed of light in any other medium is given as v. Light, when it goes through a medium, is slower than in a vacuum. The speed of light is not constant if traveling through matter. This may seem to contradict the rules in physics, where the speed of light is a constant in all frames of reference and at all times. However, the light is not going through the medium without interacting, as it would in a vacuum. There is heavy interaction, absorption of photon energy by electrons and release of photon energy by electrons going on as it travels through matter, and this gives the effect of slowing down the overall speed of light. One could think of it as the photons coming in are not the same as the ones going out, because they are being absorbed by electrons and then being recreated in a way. Common N values for materials like glass, plastic, and so on, and water are generally given for yellow light. That is because the values are variable according to the wavelength of light. It so happens that the value of N will be higher for blue light than for red light. In other words, the speed of blue light going through a medium like glass or water will generally be slower than it would be for red light. So in air, it's almost the same as in a vacuum. Air molecules are far enough apart, they do not have significant effect on the speed. However, in water, you can see that the N value is 1.33, which means that, and that is 4/3, which means that the speed of light in water is 3/4, right? Which is 1/4, 3/4 of what the speed of light would be in a vacuum. The N value goes up in the cornea to 1.38, and glass and most of the intraocular lens implants we use are in the neighborhood of 1.5. Chapter 2, Geometrical Optics and the Eye. This is the longest chapter that we will be doing, and will be done over more than one session. Snell's law of refraction. In this slide we see how waves of light are moving forward and they encounter a boundary where air meets water. Index of refraction of water is higher than that of air. As a result, the wavefront, as it moves forward, the part that enters the water first slows down ahead of the part that enters later. By the time the wavefront has entered the water completely, the direction has changed. So the direction of light, of the middle of the series of arrows shown, when it crosses the boundary, the angle to the vertical changes. The vertical is known as the normal. The angle to the normal, theta, is different than the angle to the normal theta prime after it enters the water. The relationship of these angles is shown by Snell's law of refraction. A derivation will be shown later in the series. For now, let's just say that the equation here applies. So index of refraction times the initial sine of the initial angle to the vertical is equal to the index of refraction times the sine of the angle to the vertical after moving through the water. Most textbooks will not show you the wavefronts of light. They will just show you the arrows, and they will only show you one arrow, the arrow that crosses the vertical at the point of interest on the boundary. One line here, one line here. Here we see a situation where the light is originating in the water medium, and it's going through a boundary, exiting into the air. Note that here the angle to the vertical was smaller than it is after it enters the air medium. In other words, the direction of light is bent away from the normal, as they say. Notice that in the previous slide, where light was originating in air and entering the water, that the direction of light was being bent towards the normal. In other words, becoming more vertical. This is characteristic when moving to an index of higher index of refraction. So to summarize, when going from lower index of refraction to higher, light is bent towards the normal. When going from an index of refraction of a higher index of refraction to one of lower, it is bent away from the normal. If light is originating in an index of a medium of higher index of refraction, as it is in the angle of the eye and moving through the aqueous and cornea, and trying to exit into air in one of lower index of refraction, one would expect that whatever angle is in the higher index of refraction, the light will be bent away from the normal such that its angle will be greater than it originally started as. There is a point at which, given an originating angle, the exiting angle will be 90 degrees. Anything from that point onwards creates total internal reflection such that light cannot get out to the medium of lower index of refraction. In the case of water, which is similar to the eye, theta is 48 degrees. If theta is 48 degrees, then theta prime will be 90, and there will be no ability of light to get through this boundary. For this reason, we have something called a gonioscope, and as you can see, we've eliminated the curved air-water interface because the plastic, the gel, and the eye have much more similar index of refraction to each other than to air. Therefore, the light can now exit, go straight through, until it hits a mirror inside the gonioscopic plastic compartment, and then it is redirected forward to the observer. Light has no trouble getting out through this boundary because it is actually quite vertical. What we showed before with a biconvex lens, which has a higher index of refraction than the surrounding medium, is a converging lens. In other words, it tends to take the divergent light that comes off objects and it forces them to converge, as you saw in the analogy of the runners. We call a converging lens having plus power. We can simplify the diagram of a lens by pretending that there isn't a width to it or two curved surfaces by just drawing a single line and pretending that all bending of light occurs at this one line. This approximation is better than you would think because the actual thickness of the lens and the distance between the two surfaces of the real lens is actually quite small compared to the distances usually seen between object and lens and image and lens. So in summary, all refraction is deemed to occur at an infinitely thin converging lens. So here is a diagram of a real lens which has a thickness and a curvature, and the thin lens depiction, shown by a line. We know that a lens has to have a curved surface, otherwise the dynamic of the runner's analogy slowing down as they enter the lens would not change the convergence or divergence of the light. In other words, what we call changing the vergence of light. So unlike the slide where we showed a converging lens, this diverging lens, what we say has minus power, is taking the divergent light that is moving towards it, and it's actually diverging it even more, so that an observer on this side of the lens thinks that the rays have originated from this point here. There is really no concentration of light here. In actual fact, the light waves are spreading out. But it appears that way, and we call that a virtual image. If you stand on this side of the lens, there is no virtual image. You have to be standing on this side in order to appreciate it. In other words, on this side of the lens, you see where the object is. On this side of the lens, you don't see where the object is. You see where the object appears to be, which is the virtual image. So here's an example of a biconcave lens, which made of glass, which would diverge light, and we would call a diverging lens. And this is how we represent it. The arrows are inverted compared to the ones we use to represent a converging lens. Here we see a diagram of a thick versus a thin lens. This is what's really happening, but we represent it this way. So there is some refraction here on this surface and here, but we've represented all occurring in one plane. And as I mentioned before, because the distance between the two sides of the lens is much, much smaller than between the lens and either object or image in most circumstances, one can get away with this approximation. This is a gross exaggeration of the width of a lens versus typical object and image distances. So here is another way to represent lenses. Instead of one plane in the middle, we now more accurately have two planes where refraction is deemed to occur. It is slightly more accurate because it takes into consideration the width of the lens. So here we have the light diverging, and once it reaches the first principal plane, we then just continue at the second principal plane as if nothing happened between them, and then we have it go on its way to the image point. This is the thin two-lens model as opposed to the thin one-lens model, of representing a real lens. We will not use this very much in our calculations for clinical purposes. The sign conventions used in clinical optics are as follows. In this case, the object is giving off diverging light. Diverging light is considered to have minus avergence. Here we show a lens which has converted that into converging light. Converging light is said to have positive avergence. The distance from an object to any lens is considered a negative number. The distance from a lens to the image is considered a positive number. Be careful, note that some physics books use different conventions where the formulas therefore have to be adjusted accordingly. In these books, object distance is also considered a positive number, just like image distance. But the formulas will then have to be changed in order to allow for that. In our clinical optics and in clinical optics books, distance u, which is the object distance, is considered negative. Here we see a divergence diagram with a plus lens. There is an object giving off light, which is divergent, at a distance minus u, and the convergent light ends up back at a point at a distance v away from the lens. Small u and small v for distance, capital U and capital V are used to indicate vergence. Vergence is simply the inverse of the distance in meters. So 1 over small u becomes big U, which is object vergence, and 1 over V becomes image vergence. Vergence is stated in units of diopters, as is power of a lens. Distance is in meters. This is the overriding formula that guides us in most of our calculations. We say that the vergence of light coming in plus the power of the lens equals the outgoing vergence. So taking this formula and combining with these two, you can also say that 1 over small u plus power equals 1 over small v. Here is an example of using the vergence formula. We have an object which is 1 meter away from the lens. Therefore, the vergence of the light of the object just before it reaches the lens is going to be 1 over minus 1. So vergence u here is minus 1. The power is 5. 1 minus 1 plus 5 gives 4, which is the outgoing vergence. So the vergence of the light just as it leaves the lens is now plus 4. Because we know that the big V is equal to 1 over small v, the distance here, small v, has to be 1 over 4. So we now know that the image point will be 0.25 meter away from this lens. Note that this lens has converging power, more than enough to overcome the divergence. In fact, much more, because the minus 1 became plus 4. Here is a diagram just to show how it looks with the minus lens. It's a very similar calculation. We use the same sign conventions. However, the image is on the same side of the lens, the virtual image that is, as the object. But we still have distance v, and we have distance minus u, and we still have vergence, right, the vergence of the original light, and now the vergence that's leaving the lens is the image vergence, which is the vergence v. And to the observer on this side, this light appears to be coming from this point here. The image point and the object point are related to each other by the formula, as always, the same one that we saw before.